Module 12 of Unit 2, Natural Disruptions to Ecosystems. So, in a previous module, we discussed how each species has a particular range of ecological tolerance to different abiotic conditions and how biotic interactions can further restrict where a species can live as part of their realized niche. We also saw that historic slow changes in environmental conditions of thousands of years can cause species to shift their geographic ranges as they strive to find suitable environmental conditions. So we had a example of a mouse trying to live in your newly developed house because it lived in the field, and then construction workers built that house, and then you move in with your dog or cat, and so the biotic factors are limiting that mouse from living in your house. And we also looked at those trees moving their ranges further north as the ice melted. At the ecosystem level, we have seen that flows of energy and matter in ecosystem are essential to the species that live there. However, sometimes ecosystems experience major disruptions that alter how they operate. Disruptions can occur over time in space, and the environmental scientists are often interested in how disruptions affect the flow of energy and matter through an ecosystem. More specifically, they're interested in whether an ecosystem can resist the impact of that disruption and whether disrupted ecosystems can recover its original condition. In this module, we're going to consider how environments can be disrupted and how this can affect the species ecosystem. And also, we'll investigate how these ecosystems can bounce back to their pre-disturbance condition. So our learning goals for this module are describe how natural disruptions vary over time and space, identify how Earth's climate and sea level have changed, and then finally, we're going to explain how natural disruptions can affect habitats and animal migrations. So environments change all the time. All of our environments are changing pretty consistently. Environments can be changed over the course of days, weeks, years, or millennia. So these disruptions can be categorized by their frequency, and we categorize them in three different ways. We have periodic disruptions, which occur at regular intervals. So I like to think of that as night and day, or high tide and low tide, right? So if you are living in a tide pool, then your disruptions are happening every day. Sometimes you have water covering you, bringing you food and nutrients, and sometimes you don't. Episodic disruptions, so those are somewhat regular. So I think of like El Nino, it happens on a pretty decent rotation of everybody like 2 to 7 years. And then random disruptions are no pattern. So a comet hits the Earth, a hurricane affects your island, a thunderstorm wrecks your ecosystem. One more good periodic disruption would be cicadas. So we can predict when cicadas are going to come up depending on what brood or hatch they're in, whether it's 11, 13, or 17 years. Okay, and those are our categories of disruptions. We have three main categories. So besides timing, duration of disruption plays a large role. Disruptions that have small special extent tend to occur in short duration. So usually the smaller it is, the least amount of area it affects. So obviously a thunderstorm down here at the bottom is only here for an hour or two, if that, and it doesn't affect that much area. Think of a thunderstorm in Jeff City. It's usually gone by the afternoon or the morning or whatever. Whereas if we saw a hurricane and we were living in Florida, a hurricane is going to affect a bigger area. And then if we live somewhere where monsoons happened, we would expect that to take up the majority of our ecosystem for a decent amount of time. So a month of rain would be no good. Right. And so this would obviously have very little effect on our ecosystem, and this would have a giant effect on our ecosystem. So some disruptions can actually be beneficial, such as fire removing non-adapted species. So that disruption would make that ecosystem a little bit stronger, because if the species is not adapted to fire, it would play the role of natural selection. And so anything that was genetically superior for that or had an advantage would survive, and the other things wouldn't, making that ecosystem more resistant, which means it would be unaffected by the disruptions. So there is the long needle pine, which warmer temperatures actually encourage it to germinate, which is interesting because after a forest fire, the smaller undergrowth would be taken out, which means that ground would be pretty fertile and full of nutrients, meaning that a long pine's seed would have a better chance of growing, and so that forest would become stronger. Maybe not as diverse, but it would be resistant to other disruptions. If a species is affected by a disruption, the rate it takes to return to its original state is known as its resilience. So, think of how far or how quickly something can bounce back. So, after a major event such like a hurricane or a forest fire, how long does it take that ecosystem to get its animals and its plants back into shape that it was before, or even better? So, just to reiterate, resistance is how hard it is to change that ecosystem because they are just well adapted to whatever you throw at it. And resilience is when that disruption does happen, how fast does that ecosystem bounce back? So, throughout Earth's existence, climate and sea levels have changed. There are many methods of measuring this change, especially as species compositions. So, what species are there? What is the ecosystem composed of? Gas bubbles in ancient ice, which is pretty interesting, and measuring melts of sheets of ice. So, one thing that scientists are doing is they are measuring the number of species through fossils or buildup of sediments to give us a clue of climate and sea levels. So they are actually finding these tiny little creatures called protists, and they have shells, and they are buried in levels of ocean sediment. By knowing the age of the ocean sediment and the preferred temperature of the different species of these protists, scientists can indirectly estimate the ocean temperatures and how it has changed over time. So, in the grand scheme of the Earth, humans have not been here that long, and we've been recording data like this for even less amount of time. And so, it's hard to know, or it was hard to know before scientists started doing this research, if the Earth was just going through its natural warming and cooling phases when we talk about global warming, or if there was a obvious human impact. And so, scientists started being able to give a pretty good estimate of what the temperature looked like 500,000 years ago by looking at the ocean sediment and these tiny little creatures and seeing what it looked like at that point. When snow falls and freezes through compression, it carries gases that freeze. So the tiny little gas bubbles will get caught in there, just like they do in your ice in the freezer. And these ice cores can help measure gases to see the climate and gases have changed over time. So what's happening is these scientists are going to places like Antarctica and the top of the Himalayas, and they are taking out these ice cores, which is a big cylinder of ice, and they are slowly melting it. And as these gas bubbles kind of pop there, they're able to extract whatever gases were in there and be able to tell us what the air was composed of. So carbon or CO2 or oxygen levels and that sort of thing. And they can make a determination about or better indicate the temperature that the ocean would have been or the top of the Himalayas would have been at that particular time based off of like the isotope of oxygen that was in there. So I found that was pretty interesting. And it helps us kind of better predict or see what kind of impact or disruption that humans are causing. So we ended the final or the last module talking about extinctions, and we're on the verge of the next mass extinction, or we're already there. And so, how are we actually affecting that versus what the Earth is doing naturally? I think that this graph here is pretty telling or pretty interesting, if nothing else. So we can see on this side we have our CO2 parts per million in the air or the water of the ocean. We have our temperature, and it's in degrees Celsius, so there's not that big of jumps, but obviously we know from 0 degrees to 4 degrees is actually pretty significant in Fahrenheit. And then we have our time. So parts per million seems like it follows the temperature pretty closely. There's not like a one that's like way up here and way down here as far as increase and decrease. And we can see that over time, obviously, Earth has fluctuated a lot, but in the last, less than 100,000, maybe 20,000 years ago to today, we can see that there is a real big jump in our CO2 parts per million as well as our average temperature is on its way up in maybe the last 20 to 50 years right here. Is that caused by humans? Don't know. Evidence would suggest that probably. So, past sea levels can be measured by looking for fossils where oceans are no longer present. This creates a profile for global sea levels over time. So, you can see in this graph right here, sea levels have been measured, and it's been thousands of years ago, and it fluctuates quite a bit as in reference to temperature. It seems like, right? One thing that scientists are concerned about right now is that it goes up and then it's been on a steady decline where sea levels have been sinking, which means that we're having more um, water stored up in our ice caps, which is good for keeping the Earth's temperature low. But in the last 20,000 years or so, it's risen to back above what we can be considered sea level. And that's concerning because you're losing a lot of biodiversity that way and things that depend on that ice to survive, as well as the Earth is getting warmer because it doesn't have its natural refrigerator being stored up. And so instead of having ice cubes, we just have hot water to drink, right? And so that's never good. Um, Obviously, that the sea levels have fluctuated a lot to where they're able to pull marine fossils out of places that were believed to not have marine life in there. So we can see that the water levels have changed all over the place, and now we see the opposite happening, where water is starting to take on these islands that have normally not had an issue with flooding and things like that because of the melting ice caps. So finally, how natural disruptions can affect habitats and animal migrations? Disruptions can cause large habitat changes and animal migrations. When some changes happen infrequently and rapidly, resilience can allow ecosystems to bounce back quickly, and then long, rare distributions can lead to bigger changes. So, disruptions can cause large habitat changes and animal migrations. So, if we had a big flood in those fields that are by the Missouri River as you go across the bridge, and the water just wouldn't seem to go away, instead of that being farmland now, we might consider that a wetland. And so that would change the types of animals that live there, right? And if we got enough of the marine life to come over in the flooding, you could see that those turned into even lakes or ponds, right? When some changes happen infrequently but rapidly, resistance and resilience can allow an ecosystem to bounce back quickly. So, like those forests that go through the forest fires every few years, those forests seem like they're doing okay. They're able to bounce back. It sucks for the displacement of the animals and things like that there, but it is making the ecosystem a little bit stronger. And so, to be able to survive there, you have to be able to resist forest fires, which makes that ecosystem more resilient. Right. And then long, rare disruptions can lead to bigger changes. So if Missouri suddenly went through a hurricane for some reason, we would probably just be covered in water for a long time, or a lot of our soil nutrients would be taken away through excess runoff and things like that. Right. So long, rare disruptions that we're not expecting, things that wouldn't be common for Missouri that would happen to us, would cause our ecosystems to change. Okay, so intermediate disturbances hypothesis. So this is saying like not all the time disruptions, or not long, rare disruptions, but kind of in the middle where it happens semi frequently, but not every day or not every couple of years. It explains that having intermediate levels of disturbances can help an ecosystem develop high diversity due to the buildup resistance and resilience. So, in general, we expect to see high species diversity in intermediate levels of disturbances. Rare disturbances favor the best competitors, which outcompete other species. So, that just means if there is not really any disturbances that animals have to keep up with, whoever's the top dog there is probably going to stay the top dog, and that's fine until you have a rare disturbance, and that might shatter your whole ecosystem because everything would become out of balance, right? Frequent disturbances eliminate most species except those have evolved to live under such conditions, and at intermediate disturbances, species from both extremes can persist. So, frequent disturbances mean that there is no true top dog until you start developing ways around it. But intermediate means that it keeps everything kind of in check. So you can have more species richness and evenness without there being a dominating species that just takes over everything. One example that your book gives is snails eating algae, and that's what these graphs are right here. So, species richness of algae, you can see the more rich it is, the more snails it can support in an area. But if it has to support infrequent amount of snails over here, then the algae is not very high, and the species richness of the snail is not very high. If it has too many snails, then the richness of the algae goes down because it's not ready to be taking on that many disturbances. But if there's a sweet spot right in the middle where the density meets the richness of the algae, so there's enough food being able to live and grow to support the consumer in that situation. So we want immediate disturbances to keep our ecosystems healthy and resilient and resistant. Yeah, so seasonal change can lead to species choosing to migrate rather than overall adapt. Migrations can lead species to where resources are more abundant, predators are less common, or conditions are more in their range of tolerances. So the example that your book gives is it is following these animals around the Serengeti National Park. And depending on the season, these animals will be in different spots. So typically, I think the zebras will follow the wet season because there will be a higher diversity of plants that they like to eat, and they only eat a certain part of the plant. And then following them will be the antelope or the deer or the dik-diks. They like to eat the same plants, but just a different part of them. And then finally have the wildebeest who will kind of be traveling along, eating the lower parts of those plants, getting the different types of nutrients. And so it's kind of neat because they don't really compete with each other, even though they all serve the same niche. And so animals like the zebra will start here January to March, April to June will move here for the wet season, and then go back down, and then eventually it'll just end up where they already were, which is pretty interesting. And all that is just based off of the disruption of a wet season versus a dry season. With that, that is your module 12. If you have any questions, please reach out.